Introduce Professor Kerry Vahala. I'll just mention that this talk was organized entirely by, I don't want to say NIST specifically, but by the student group, OSA, the student OSA chapter at University of Calgary. So I just want to thank them for putting together this fantastic list of, series of speakers, including Kerry. So Professor Vahala is the Jenkins Professor and Professor of Applied Physics at Caltech. And he is widely known for his studies of devices called optical microcavities and their application to a wide range of subjects, including miniature frequency and time systems, microwave sources, parametric oscillators, astrocombs, and gyroscopes. And Professor Vahala has made early contributions to the subject of caveat mechanics. So I think some of the papers from his group really lay the groundwork for a lot of what's happening today in caveat optomechanics. He's a member of the National Academy of Science and Engineering, a fellow of IEEE and OSA. He received the Alexander von Humboldt Award for his work with high-Q optical microcavities, a NASA Achievement Award for application of frequency combs to exoplanet detection, which is some relatively recent work. The OSA Paul F. Foreman Team Engineering Excellence Award for a 2-photon optical clock. And he was also involved in the early efforts to develop quantum well lasers for optical communications, for which he received the IEEE Sarnoff Award for his research in quantum well laser dynamics. He's also worked in the field of cavity QED, and I would say just in general has consistently really elucidated clearly, the important physics that underlies a lot of the most interesting applications of optical microcavities, as well as advanced or they're state-of-the-art. So with that, I'll hand the screen over to Kerry and look forward to hearing what his latest work.
Yeah, thank you very much, Paul. And so I want to thank Anastup for for organizing and all the logistics. Let's see if I can get the, there we go. Yeah, so very happy to be here and to share with you some of the recent developments in one of areas we're working a lot in these days, which are frequency microcombs. And as Paul said, we generally work in the area of high-Q microcavities, and there's a lot of different interesting applications, but this is one that has really taken off in the last 5 to 6 years. And so I want to tell you, I guess maybe the big message I want to leave with you today is this idea of unification of the optoelectronic spectrum, and particularly at the chip scale. And I'll be giving you some of the physics of microcombs, obviously, and kind of take you on this kind of interesting story. But I wanted to, because it might be just a little bit obscure, I wanted to first of all begin by explaining what I mean by spectral unification. And I'm going to do that in 2 parts. First of all, I'll look at some examples that are familiar to everyone, where technology that has been around for many, many decades has allowed us to unify different particular segments of the electromagnetic spectrum: audio, radio, microwave. And I'll pick two particular examples. Then we'll move on and show how this is now possible, has been possible really for the last 20 years using frequency combs. So we'll sort of extend or generalize that idea. And then I want to get into the core of the talk, which is really describing how these frequency combs are being miniaturized, the physics of the devices, and then huge effort underway right now, looking at integration of comb systems, system demonstrations, which are really interesting, and then kind of return to the basic message of the talk at the end, and kind of maybe hopefully paint a vision of how this is going to impact technology in the coming decades. So let's start up the top, and I'm going to begin again by just giving you some familiar examples of electromagnetic unification. Okay, maybe we don't think about it this way, but this is the way I'm going to try to describe it for you. And so first example is a microwave or radio frequency synthesizer. And everyone uses these in the lab. You can buy them commercially, and very handy tools. And so on the left side of this chart, I'm showing what they do. They basically, a synthesizer today as a little box, and we type in, or we actually just feed it information from a computer that gives it a certain number of significant digits, and its job is to basically create a sinusoidal waveform at that frequency to fairly high level of precision and accuracy. So I'm showing a few of these sinusoids that would be generated in a synthesizer. If you look at the inside of a synthesizer, electrical synthesizer, this is one version. There's actually some other versions, but in this version, there's basically electronics, mainly dividers. Okay, so you see divide by M, divide by N, phase comparators, low pass filters, but this electronics link together a low frequency oscillator, which is a reference, and a high frequency oscillator, typically a microwave oscillator, which is the VCO here. And the electronics phase coherently links them together and then processes and uses the reference to establish the stability of the system, but uses the higher frequency VCO, stabilizes the VCO, but then uses this VCO in combination with this improved stability of the reference to then synthesize the frequencies that you need. And so the output will be some fractional ratio of could be a of the reference frequency in this case. And so this is what they do. And as we'll see, as I'll come back to in just a moment, frequency combs basically are an optical equivalent to all of this electronics that you see in here that is actually connecting together the low frequency reference to the high frequency reference. So kind of just keep that in mind. All right, now here's another example. All right, so the first example, the synthesizer began with a reference that was a low frequency reference and then connected up to a high frequency oscillator. Here, I'm going in reverse. And, but again, this is another example of kind of, if you will, electromagnetic unification that we take advantage of in many, many different technologies today. So this is a clock. And all modern clocks, including the ones that we use for time standards, the global time standard, the cesium atomic clock, work on a very simple principle that is illustrated using this wristwatch. And so this wristwatch, I dissected it. And if we look inside, you can see the battery. Here is the liquid crystal display. Behind the liquid crystal display, there's some electronics. I'll come back to that in a moment. And there's a little cylinder here. And if the cylinder is opened, there's a quartz oscillator in there and a quartz crystal, quartz tuning fork. And so the principle of operation of the little wristwatch, which is the same, even for the very advanced, atomic clocks, is that the quartz in this case provides the reference. And these little tiny quartz crystals or quartz tuning forks are actually designed, they're trimmed to oscillate at 2 to the 15th hertz at a particular temperature. And the electronics inside the watch actually divides by 2 to the 15 times. So you now have this very, very low frequency output in this case that gives the second of the click. And so, the clocks, the accuracy of a clock is entirely dependent upon the stability of that tuning fork, which is why we've been drawn, over many decades towards atomic references as standards. So this is again, kind of coming back to the basic theme, this is an example of unification where we're going from a higher frequency to a lower frequency. Admittedly, the high frequency in this case is just a little higher than audio, so not particularly high. Okay, so that's spectral unification, but now let's turn our attention from audio, radio, microwave over to optical and electronic. And how does this happen? Well, the first thing I want to make clear is that the kind of unification that we're talking about here is not, the unification that, or is not a connection that already exists and has been available for many decades, associated with, for example, detection of light waves. So we obviously could detect a modulated light wave, and we could create a modulation in a current, or we could go the other way. We could apply, a modulated voltage or current, to a phase modulator or an amplitude modulator, and then impose that electrical signal onto an optical carrier. And so I'm not talking about that, but I'm talking about, and again this carries through this theme that we saw with the synthesizer and also the clock, is that we literally want a coherent bridge we would like to be able to start with optical signals, that are running at hundreds of terahertz and divide them down to create radio frequency rates, or run the other direction. We start with radio frequency signals, multiply them up to create optical rate signals. And with this in mind, it's very obvious what the problem is and why this is was so challenging. And it's the fact that electronics simply cannot operate at these tremendously high frequencies of optics. And so a microwave circuit is still 10,000 times slower than an optical transition in an atom, or or something that might be typical of a telecommunications laser, for example. And so this is a huge technological feat in order to make this coherent bridge. All right, but what's interesting about it, and this is kind of dipping back into history, is that very soon after the invention of the laser, and lasers we can think of, even though they, the physics of a laser is quantum mechanical, at a certain level, we can think of a laser oscillator as a kind of optical equivalent of a radio frequency oscillator. It's like the sort of the manifestation of this idea of regenerative oscillation, but now at optical frequencies. And so with the laser, with the invention of the laser, groups started to think about this very problem. Okay, how could you bridge a radio frequency signal with an optical signal coherently? And this led to this very interesting sort of long history. It unfolded over about 40 years, beginning in the 60s, all the way through the year 2000, of devices called frequency chains. And maybe you've read about them. You don't read about them so much today, but if you look in the literature, you'll see many publications on frequency chains through this period. And the idea was to start with a radio frequency signal and then to multiply it and to keep multiplying it in steps. At first using maybe electronics, but then ultimately optical nonlinearities. And so this is a very tedious process, and but it was done. It was actually successful. Several groups around the world. This was actually a frequency chain I'm showing over here that was developed and demonstrated at the National Bureau of Standards, and today that's NIST, the National Institute of Standards and Technology in Boulder, Colorado. And you can already see that this is a large device. In fact, this was probably just one part of the device. I think the actual device probably occupied several laboratory bays. And there were efforts, as I said, in Europe and other places, building these chains. And they were ultimately successful in making the bridge, and there was actually interesting science, that was possible as a result of these chains. But you can see that any kind of, practical application or any kind of widespread use of these chains was not going to be, possible just because of the sheer size, and they were also not very tunable. And so there were several serious, technological limitations, I would say, associated with these, even though they were ultimately very successful. And so all of that, the kind of exciting development, which happened, just a little over 2 decades ago, was actually the development of the frequency cone, which I now want to kind of explain real quickly. And in a nutshell, frequency cone is a device that is going to allow the connection, the bidirectional coherent connection of electronics with optical rate signals. And those optical rate signals could be, a laser signal, could be an atomic transition. In fact, it's now possible to use frequency combs. It's been possible for quite a while, to literally count, to count the optical cycles, of atomic transitions. And so this is a very revolutionary, development, and has opened up a gigantic, number of new possibilities in science and technology. The importance of it was quickly recognized, and so half of the Nobel Prize in Physics in 2005 was shared by Ted Hensch and Jan Hall for the invention and the subsequent, applications of the frequency cone. And so let me tell you just a little bit about what's involved in the frequency cone, because that side of it is very curious in its own right. And no doubt several of you are work with frequency combs, and so apologies for the little bit of review here. But the most surprising thing, to me, about the frequency comb is that actually it's using a technology that was actually invented decades before. And that's the mode locking process, okay, mode lock laser. And so this is a little animation showing a titanium sapphire, meant to be a titanium sapphire mode lock laser, which was one of the first early frequency comb devices. And so it's phase locking all of the modes, longitudinal modes of this cavity to create these very short pulses. And through a process called self-referencing, and this is really the key to the frequency comb in the modern way that we think of a frequency comb, through a process called self-referencing, it's possible to actually anchor, okay, literally coherently link all of the frequencies, the discrete optical frequencies that make up those pulses to a radio frequency signal. And the technique, I'm going to quickly go through it here, is shown here. So this is meant to be, the Fourier spectrum of these pulses. So there's a very short pulses coming out. In the Fourier domain, we'd see all of these little lines. The lines would be separated, obviously, by the repetition rate, the free spectral range, if you will, of the cavity. And so any one of the lines could be indexed. We could have a frequency f sub n, where n would be an integer. Here would be the repetition rate. So we'd multiply that by the or multiply n times the repetition rate. But there's an extra little frequency here, f sub 0, that you need to also measure. And f sub 0 can be thought of intuitively as a kind of fictitious comb line number. It's the n equals 0 comb line number. And the real, I think, key idea of the frequency comb, the self-reference frequency comb, is this technique for measuring f0. And this is how it works. First of all, the comb spectrum itself needs to be broadened. And so there's a broadening that I'll show in just a minute, one of the typical ways to do that. But it needs to be broadened to roughly an octave so that a few lines down here at this end of the spectrum can be sampled, can be doubled using a nonlinear crystal, using typically piplin, periodically poled lithium niobate. The doubled replicas are then compared with the higher end of the spectrum up here. And compared means simply heterodyne detect the replicas with the original lines that are here, roughly an octave away. And you can show in just one line of algebra that the beat frequency will actually be f sub 0. And so this process of self-referencing means that f0 can be measured, f repetition rate can be measured. Each of those can be controlled, okay, by, can be, servo controlled, but using various cavity parameters, and stabilized to a very stable radio frequency signal. And so in the end, what has been accomplished here is that a radio frequency, very stable radio frequency, it could be a maser, okay, for example, or just a good quartz oscillator, can be used to actually anchor all of these lines modulo the line spacing. And so this idea was revolutionary in the sense that it launched, a whole, improvement. I mean, not improvement, but revolution in spectroscopy, even new techniques that are now used, as a sort of standard spectroscopic tool. I'll come back to those in just a moment. But what was equally important was that actually this represented only one mode of operation of the comb. In fact, there were two others that are just as important. And each of these three different modes of operation have their own completely different application space. And so this was, in the end, you can think of a frequency comb, a self-frequency comb, as almost like, if you're familiar with the terminology of a Swiss Army knife, where a Swiss Army knife is this, a very versatile tool that you can take, backpacking, and it has all sorts of different, interesting, important functions. And the frequency comb is a little bit like a photonic Swiss Army knife. It has just an incredible array of different functions. And just to kind of show you how that works, this is a little diagram that is providing a kind of mechanical analogy, right, of what the frequency comb is doing once it's been set up in this self-referencing configuration. And so here I'm not looking at a TISAF, but this is a Fabry-Perot. So here's a series of these longitudinal modes, of the Fabry-Perot, and there's some kind of mode locking mechanism that has been introduced, and so pulses are being formed here. They're not very narrow pulses, but they're pulses, and the way we have them diagrammed here. And here's the repetition, or the period between the pulses is 1 over the repetition rate. Now, the comb, the frequency comb, once it's been configured in this special way, through self-referencing, plays the role of these gears. And kind of let me explain the idea. So the mode of operation that I just described, whereby I'm going to inject, or use maybe perhaps a maser, and I'm going to transfer the maser stability up to the comb lines. That's what's being illustrated here as, the red, arrow. So this would be configuration 1. And so here you can imagine there's this very stable radio frequency signal that's driving the microwave gear. And then the frequency comb is now connecting up that stability in a phase coherent sense, to hundreds of thousands, even about 1 million different lines out here, these comb lines that are now extending out over an octave. So that's mode 1. That would be this sort of spectroscopic mode that I inferred or mentioned. But there's another way. Mode 2, you can set up the comb a little differently. And that's this green arrow. And now one of these comb lines, these are now the optical frequencies, those could be stabilized. One of those lines could be stabilized to something very stable in the optical domain. Could be a very stable reference cavity, or the best stability that we have now available in the optical domain would be cold atoms, or lattices of atoms, cold lattices of atoms. And so those long-lived, very cold systems actually can be used as references, and their stability can be transferred down to the microwave range. And that's how you create these the very, very best clocks that we have right now. I'll mention them just a moment, or talk about them in just a moment. So that's mode 2. Mode 3 is actually a very interesting one, that once this is all set up, and there's an octave, or it could be even more than an octave, of these lines here that are very closely spaced together. They can be just radio frequency rates away. This provides a way of transferring coherence between different systems. And it might be that an experimentalist is interested in studying very, very accurately optical transitions that are occurring in one atom against another atom, maybe testing fundamental science, the predictions of fundamental science, perhaps some very basic scientific questions this way. It may be that you're interested in simply transferring coherence between two clocks, two of these optical clocks I referred to a little earlier. And so this is a third very powerful mode of operation. And so kind of coming back now to my original theme of the unification. So combs, really almost overnight, literally within a year after their invention, it became clear that what they were going to do is they would replace the chain. So this very, very cumbersome chain, frequency chain that existed before, was now replaced by the frequency comb. We think of this mode of operation of going from radio to optical as synthesis, because it really is. What we're doing is we're synthesizing optical frequencies. And I'll show you a synthesizer a little later based on these new miniature combs. The other direction, what I talked about, the wristwatch, the clock. Well, now this happens at in a much higher frequency. And so the very most accurate clocks, these are called optical clocks, now use cold atoms or cold lattices of atoms and transfer that stability down by anchoring one of the comb teeth and then dividing it down so that it can be literally counted. And the counting process in this case is very easy. You simply detect the pulses from the comb, and now there's a radio frequency signal, an electrical signal that can be then further divided down, with electronics. And so these are the optical clocks. They're about 100 times more accurate today than the cesium time standard. So they will be the future time standard, for the world. It's also kind of interesting to note that the very, very best microwave and radio frequency oscillators are now based on this process. And so this is a huge victory, for optics. This is a case where optics has now really intruded or entered, the domain, of electronics. Where electronics was once king, optics has now replaced it. And this will be something that, optics will continue to sort of, replace and dominate electronics at the level of oscillators, in the future, radio frequency and microwave oscillators, just because of this process. All right. So now I've given the background here. I've explained spectral unification. I've explained how frequency combs now have greatly expanded spectral unification between photonics and electronics. Okay, these, what seemed like an insurmountable gulf in frequency is now bridged, okay, bidirectionally and coherently, okay, by these frequency combs. And these frequency combs, I have to say, they're not that large. So they started out as tabletop devices, but probably as many of you know, you can buy commercial frequency combs. And they're kind of like shoebox size devices now. They're rack mount size devices. They're not, they certainly do not occupy a lab base. So they have literally revolutionized, many, many subjects just because of their availability and their convenience of use. But now let's turn the question to, could we do more, and can we further miniaturize the combs all the way down to the chip scale, so that instead of building boxes of combs, rack-sized combs, suppose that one day combs could actually be in a butterfly package. And I hope to leave you with the impression, in fact, not the impression, I hope to convince you that in fact that day is not that far away. And so let's look at how that's happening right now. Okay, so first of all, return to this, important point of how a frequency comb works. There's a, showing now a little more detail. So here is again the titanium sapphire comb, and which is mode locking away. A commercial comb is going to broaden, okay, those pulses using typically a piece of nonlinear optical fiber out to an octave. And then there'll be some, nonlinear elements over here, like I said, lithium niobate in particular, that will allow the completion of the self-referencing process. And so if we look at this has really been the stumbling block for quite a long time in terms of miniaturization. And I'm going to spend most of my time today. In fact, if I had more time, I could tell you a little bit about some of the other elements here. But most of the time today, I'm going to spend looking at the so-called microcomb, and the microcomb meaning the device that is now being used to generate very, very stable, very narrow, temporally narrow pulses on a chip. But I'll begin by noting that in fact all of the other functions that are required, to complete the self-referencing are available, and indeed they have been demonstrated in just the last 5 years. Just because of the importance of this process. And so I'm listing them here, besides the mode locking, octave span generation. In fact, there's a very, very clever way of doing the octave span generation inside the cavity itself. I'll show you an example of that a little later. Harmonic generation, all the detectors, the amplifiers, all of these things are available on chip. And so we're moving very rapidly. In fact, there's a example on one of the later charts that will give you an idea of what the current size of a complete self-reference comb system is. It's actually quite small. All right, but let's look at the microcomb itself, the mode locking. And here I want to spend a little bit of time just talking about the physics, which itself is very interesting. It involves solitons, optical solitons. So back up a little bit before we get into the mode locking and the soliton generation. The platform that's used to actually create these little microcombs. I'm showing many of the different examples from groups around the world here, and these are whispering gallery resonators. And whispering gallery resonators are, many of you are familiar with them, but in case you're not, they're devices that confine light typically in a circular path. And so this little green orbit is meant to be such a path. And they do that by quasi-total internal reflection. So there's going to be a waveguide or path that will be in a high effective index material surrounded by a cladding that will be in a low effective index material. So this is silica, for example, and this is obviously just air or vacuum. And so it's confining the light. And all of these, geometries do that. And some of them are, more sophisticated than others in the sense that some of them have waveguides that are built on chip. Some of them are, I'll show you some later that are now completely CMOS compatible. In fact, they're actually fabricated in a CMOS foundry. And so this is, one part of the story. And the round trip condition that leads to, the eigenfrequencies, the optical frequencies in the cavity, it's very simple. It's simply, we want to, pack in an integer number of wavelengths, okay, in the material. And that in turn sets up the resonant frequencies, which are approximately equally spaced in frequency. You know, there's some material dispersion and so forth that, and also geometrical dispersion, but they're approximately equally spaced. All right, now the next step in making a frequency comb or microcomb is that we need to lower the loss of these devices. And so making the whispering gallery resonator itself is not that difficult if you have access to a clean room, but lowering the loss has taken, you know, quite a bit of time to work out. And, you know, 20 years ago, there were not many platforms available, you know, that could do this. Over the last 20 years, in particular the last 10 years, there's been a lot of progress in actually lowering loss in many different systems. Why do you want to lower loss? Well, because, you know, as in any kind of oscillator system like this, lower loss means higher Q. Higher Q means longer storage time. And so very simply, if we couple power in, for example, on a waveguide like this, it can show very quickly that the circulating intensity inside the cavity is going to scale like the quality factor over the mode volume. Mode volume is small, if quality factor is high, then the circulating intensity can be very high. And so, for example, if we look at that toroid here, if light is circulating in this toroid, this is a particularly small device. You see as a 500 cubic micron mode volume. The Q is, you know, over 100 million. A milliwatt in, okay, of coupled power, which is easy to do, will generate over a gigawatt per square centimeter of circulating intensity. And so that's much more than is necessary to actually, you know, achieve or, you know, be in a regime where nonlinear optical effects are accessible. And so what are the nonlinear optical effects? Well, there are many. But the one that we're most interested in today is the Kerr effect. And so I want to talk about it, a very interesting set of experiments that were, you know, done quite a long time ago. This is over 15 years ago. And they were, you know, showing one of the sets of data here. And I'll explain why this is related to the microcomb in just a moment. But this is the Kerr effect. Okay, so obviously the intensity dependence of refractive index. Okay, so all dielectrics have this property. It's a third order nonlinearity. You can think about it in many different ways. If you think about it in at the kind of the photon level, two pump photons would scatter elastically and exchange energy, and there would be what we call signal-Idler pair. That signal-Idler pair, you know, you can actually show there's, you know, they'll be entangled. And so there's a, you know, there's a process, there's some interesting quantum physics here associated at kind of the level of just producing these pairs. I'm not so much interested in that as I am in sort of going to the classical limit. And here you see a pump wave that's been coupled in on a particular resonant frequency. And you can show that that basic process leads to coherent gain, parametric gain. And the gain will lead to oscillation on a signal-Idler pair here. We have the signal, the Idler, they will be equidistant in frequency away from the pump because this is a elastic process. And there'll be a threshold. Okay, there's a gain. This is just like a laser in some sense. It's just it's an oscillator. It's a parametric oscillator rather than a stimulated oscillator. And so that it's a thresholding process, and the threshold is very low. And so this is data taken on this little microtoroid, and the loading of the cavity was being changed, so the Q was being changed, and there was an optimal loading point. You can see that the threshold where these waves would begin to oscillate was, you know, just a few hundred microwatts. And so that's kind of important because that means you can drive these oscillators with a laser that would be a 3.5, you know, laser. In fact, you could potentially integrate this. I'll show you integration just a little later. Now, the threshold, it's interesting. The threshold, I've talked about resonant buildup in the cavity, but the threshold itself actually benefits twice, okay, from Q. There's a resonant buildup effect, just as we mentioned in the previous chart, but the turn-on threshold, the amount of loss in the cavity that we need to overcome with parametric gain, that loss itself is inversely proportional to Q. And so there's a quadratic benefit in these oscillators to actually having higher Q. So a 10-fold improvement in Q, for example, leads to a 100-fold reduction in threshold. And it turns out this is the threshold for these new microcombs. And so the turn-on power for the microcombs is inverse quadratic with the Q. In fact, a lot of the other properties, it turns out the bandwidth, okay, of the microchromes, they also scale and they benefit, okay, from lower threshold. So there's been a huge effort, okay, targeting Q in a lot of different platforms, and especially the last 5 years, just because of this interesting scaling. All right, now let's continue. All right, so I talked about the onset of threshold. Let's look at these two other waves here. So I've called this signal prime, idler prime. These waves are not generated by parametric oscillation. They're the result of cascaded forward mixing. And so once these three waves are oscillating, the Kerr nonlinearity, this third order nonlinearity, allows all of these frequencies to mix, and now you start to get new products, new mixing products. And so if we go to this little animation, this is kind of explaining what happens. Inject a pump into a cavity, for example, this little microtoroid, pump a little bit to achieve parametric oscillation, keep pumping, and now many lines will form. And so this idea, okay, that actually this cascading would create all these lines, this led, okay, to the idea, the concept of a microchrome. And so this goes back to a paper in 2007 by Tobias Kippenberg's group. And so this set in motion a lot of interest, okay, in this idea, could we miniaturize a frequency comb? Because by 2007, frequency combs were, it was clear they were already very important, as tabletop devices. The idea that they could be miniaturized was very exciting. There was a lot of work that went on. The thing that was interesting, because we were involved in this at this time, is that these early combs, it seemed clear that there was a missing ingredient, and it took a while to understand what was going on. And the missing ingredient was that in addition to cascading, we needed something else, and the something else had to do with what we'd almost call pure mode locking. And I want to tell you about that. And so it took about 7 years. It was really a period of time, about 7 years, until actually we went from these cascaded devices to the modern soliton microcomb. And it's been really in the last 5 to 6 years that all of the work, I say most of the demonstrations have actually occurred. So what happened is, you can kind of see here, is that there's actually an ambiguity in the formation of these cascaded devices. They can come up in many, many different states. And what is needed is there has to be some kind of enforcement mechanism that ensures a unique temporal state, and correspondingly a unique spectral state. And the unique temporal state is a pulse. And so if you have a way of enforcing a unique temporal state, then what happens is that there's only one way to phase lock, okay, the system. And you can see these very, very beautiful, these are comb spectra that have been demonstrated, and these were really early results going back about 5 or 6 years ago. The typical kind of comb spectra that we see for what we call a bright soliton is a hyperbolic secant squared, and here's the pump wave, and this is this is really representative of all of the comb results or microcomb results you'll find today. And this has worked so well that now there's probably over 15 groups worldwide that are now studying and implementing, okay, these soliton microcombs in different platforms and studying many different applications. Okay, so with that, I now want to talk just a little bit about the physics of these solitons. And this physics is very similar, but to the solitons that have been studied for decades, going back to the 70s, really the 1970s, in optical fiber. But there are some important distinctions that I want to call your attention to. The most important distinction is that actually these are coherently pumped solitons. And this idea of a coherently pumped soliton really goes back to a paper in 1993, and in which this idea was first proposed. But the solitons themselves, okay, this new kind of flavor of optical soliton wasn't realized experimentally until 2010, and it was actually in optical fiber where this first was, they first appeared. So what happens? Okay, what's the story with the optical solitons? Well, this is the nonlinear equation of motion. Actually, one version of it that we use to study these solitons is called the Lugiado-Lefebvre equation. If you look at the part that I have circled here, you can see this is a nonlinear Schrodinger-like equation. So very typical to the kind of equation that would be used to study soliton propagation in optical fiber. There's a, so here's the slowly varying field. Here is the dispersion, which I'm showing in this case is just second order anomalous dispersion. This would be for bright pulses. Here's the Kerr nonlinearity. And if you're thinking quantum mechanically and looking at this as a Schrodinger equation, then this is a style of Schrodinger equation where the pulse, if you will, or the particle is able to essentially write or create its own potential well, through this, in this case, the Kerr effect. And so this writing of the potential well is what actually is compensating the dispersion. The dispersion would obviously be the kinetic energy, okay, in the Schrodinger equation. So you see this sort of, this is the key ingredient in bright soliton propagation in optical fiber. What is new is happening over here. And these are some terms you typically do not see in optical fiber solitons. So the first term is this loss term. This is the loss rate of the solitons. It's caused by absorption in the microcavity, scattering, intentional coupling of the soliton, the useful coupling of the power of the soliton out onto the waveguide. And we've already talked about parametric amplification by the Kerr effect. And the important feature of the new solitons is that they come with their own built-in gain, and it's parametric gain. And so the losses are compensated by the Kerr effect. The Kerr effect also compensates the dispersion. And so these solitons represent a regenerative, parametric mode lock system. And no need to dope the dielectric. It's everything is there. It's all accessible, assuming that the Q is high enough and the dispersion is engineered to have the right sign. Okay, a few other points. Okay, here's the pumping term. So this is a field that's you're going to supply the solitons with their energy. And now what I want to do is show you how we actually turn on the solitons. And to do that, let's look at this little detuning term right here. So this is this little delta omega defined as omega 0 minus omega p. Omega p is the pumping frequency, so that would be the frequency of this field over here. And omega 0 is the frequency of a mode in the whispering gallery resonator that will be pumped. And it turns out that the sign of this detuning needs to be positive, and so it's important that the pump ultimately is red detuned, okay, a little bit from the frequency of the mode that's going to be pumped. And I'll show you how that works below. So this is a little plot where let's assume first that the Q of the cavity is low, or maybe the Kerr effect is very weak. And the gray curve is meant to convey the intracavity resonant buildup as we tune the pump. And so delta omega is going to be scanned, and 0 corresponds to the pump being exactly on resonance with the cavity. And so here's the resonant buildup. Now, let the Q increase. So the optical Q increases, the resonant buildup can increase, or maybe the Kerr nonlinearity is very large to begin with. What will happen is that a result of this term over here, if we were looking at this in a static, from the point of view of a static solution, this curve would pitch over. And you can immediately see there's a bistability region over here. And it turns out this bistability region, there's going to be instabilities over here. And these instabilities are actually naturally going to lead to soliton formation. And in fact, what happens, and this is how we do this in a lab, or how we used to do it, is that the pumping frequency would be tuned, beginning from the blue side and scanned to the red side. It would, the pump laser would tune up this hysteresis curve, and then at some point it would drop. Okay, it would suddenly drop, and then there would be a step that would appear as the tuning continued, and it would finally drop out altogether. Now, this is data. Now, this shows time, but actually think of frequency here, because the pump frequency is actually being tuned from the red, from the blue to the red. So it's riding up the hysteresis curve, and here is a step. This is an experimental step. And I want to show you actually this dynamically, how this works. All right, so this is actual data that was collected using an ultra-fast coherent sampling experiment or measurement setup. We're going to plot, this is actually the tuning, again, in time of the pump frequency. So it's going to go from blue to red. You'll see it in just a moment. This is the reverse of what I was showing on the previous chart. So this is the transmitted power past the resonator. It's not the resonant buildup. And so it's going to decrease as more pumping power is coupled into the resonator. There's a lot of noise here, but there's 4 steps, not 1 step, but 4 steps. I want you to watch this ring, okay, down here. We're going to superimpose the data down here that we took, okay, generating solitons in this little silica ultra-high Q resonator. So here's the experiment. So the pump is going to come in. We're going to be resonant. You'll start to see all of this noise that forms. If you would watch this on a spectrum, it would look comb-like. We call it comb-like. We call it a noisy comb. But eventually we're going to go into hysteresis regime, and here you see 4 solitons. We keep tuning. You see 3, 2, 1, 0. All right. And in the solitons you see are nicely, they're flying in formation. There's some interesting physics there that I don't have time to talk about or why they do that. But the point that I'd like to talk about, because it's very important in terms of understanding how, to make a practical comb, and it's obvious once you see this, is that it's essential for the pump frequency to be able to jump into one of these steps. If you want 4 solitons, it's necessary to jump here, 3 here, 2, 1, but you have to jump there. And even more important, it's necessary to find a way of holding the pump frequency at a particular offset, okay, frequency relative to the mode that's being pumped. 5 years ago, that was very difficult. Okay, that was really tricky to figure out. In the subsequent years, many different techniques were discovered and used and implemented to do this, but they were, as you can imagine, they all involve servo control. There's a lot of servo control in doing this. I'm going to show you in just a moment that all of the difficulty has recently gone away just in the last year and a half. And now this happens automatically. And this was really a very important step in the evolution of these microcombs, to very practical chip-based systems. And so now it's literally possible to simply turn on a pump and then the solitons actually form. Before I show you that, though, I want to just come back to this Lugiato-Lefebvre equation. And Lugiato-Lefebvre equation, we use it to actually simulate and design combs. This is a really simple example. This equation can be dressed up a lot. We can have high order dispersion, Raman, and so forth. And this is the comb spectrum. We're going to start with a single pump frequency. This is the temporal domain, and this is going to be in the frame of reference of the soliton. So we'll follow the soliton around. And again, the pump is going to be tuned. You'll see the noisy comb form over here. And eventually the soliton spectrum will form. It's a hyperbolic secant squared. And you can see the little pulse forming over here. And so this is a really powerful design tool that is being used in the design of microcombs these days. All right, with that, I now want to go through integration and system demonstrations real quickly before concluding. So now I mentioned, how to turn on a soliton. And obviously we need a pump. We need to worry about this, how to jump into the step and so forth. And there's been an evolution of progress here. And it's culminated in some experiments I'm going to tell you about right now. And these experiments have involved a collaboration between John Bauer's group at the University of California, Tobias Kippenberg's group at EPFL, and my group at Caltech. And these are showing some really nice EPFL silicon nitride resonators. These operate at microwave rates. It turns out that's kind of a challenging thing to do. They have to have very high Qs in order to do that, forming solitons. These are some really beautiful pump lasers from UCSB. And the first thing I want to point out is that these have all been packaged together in a complete microcomb system that's fully pigtailed. And so this, you can turn it on and it will actually generate a comb. It's not a self-reference comb. I'll show you a self-reference comb in just a moment. But this is essentially giving you the mode locking right here, and it's showing that mode locking can operate to this scale. Coming back though to this problem of how to lock the laser frequency to the comb, and more importantly, how to get the comb to be deterministic. Okay, when we turn it on, how do we get through this step and hold the step and so forth? It turns out there's been an evolution in doing that. One of the key ideas was actually introduced in a paper in 2015, and it was to allow, the resonator to feed back into the cavity. And this creates a kind of we call self-injection locking that goes on. There was later work at Columbia okay, that showed that this was an efficient process, and you could actually operate this device, using a battery this way. And the work that I'm going to show you now, we actually have taken this a step further and shown that actually the physics of the interaction, the nonlinearity in the cavity, the Kerr nonlinearity, when it cooperates, okay, with the laser interaction, actually creates an entirely new operating point, okay, for the system. We call it the turnkey operating point for turnkey soliton generation. I'm kind of giving you an idea of that here. This is the hysteresis curve, again, that I had up a little earlier. And this dashed line, this is a dashed line that actually you can think of it as almost like a load line. And the load line has a tilt to it. It has a slope simply because of the existence of the Kerr nonlinearity. This is how the Kerr effect is actually impacting the laser pump. And it's forcing the system to actually operate or start its operation here. If the interaction were not allowed to happen, if there was an optical isolator, for example, placed in here, that line would be vertical. And we'd have the sort of standard hysteresis behavior. And so what this does is it makes the whole turn-on process happen automatically and deterministically. And here we're showing the laser turning on, the soliton turning on, and this is the soliton repetition rate in this case, which we're measuring. This is about a 20 gigahertz soliton. And just to show you that it's deterministic, here's where we are going on, off, and we're measuring the soliton repetition rate. And so this is all done with this little package device. This is something that's literally impossible to do, okay, without, okay, this process. And it kind of curiously, it's important. This actually involves just removing the isolator. So you do that, and you get this, this benefit quite naturally. One thing I'll mention is that I kind of alluded to this a little earlier, but it turns out that there's an entirely different flavor of soliton. It's called a dark soliton. And instead of using anomalous dispersion, we use normal dispersion. And these are some dispersion curves that have been measured in these little resonators down here. And these are devices that are being fabricated with the Bowers group. Okay, this is an 8-inch wafer. And they actually form these nice dark soliton spectra. And here you can see the repetition rate. And I kind of mentioned one other thing, and this is kind of now showing you how quickly this technology is evolving. This is really a very important result, I think, in at least in my thinking, is that these 8-inch wafers are now accessing this so-called, very, very high Q regime, sometimes called ultra-high Q. And you can see the histogram of Qs, okay, across this wafer. Many of these devices are over 200 million Q. And this is really a CMOS process right here that's being used to do this. And so these resonators can be mass fabricated, can be packaged together with 3.5 devices. And so this is now, really speeding along, I would say, the development of full soliton systems, okay, in a sense. All right. Now let's look at integration real quickly. And sorry, we've talked about integration. Let's look at system demonstrations. And I'll talk about a few key ones there. And then outlook. All right. Well, not surprisingly, once the idea, or once it was clear that, these little soliton microcombs were around, it was a natural next step to actually test them in various, applications, kind of traditional frequency comb, tabletop frequency comb applications, of which there are many, many important applications. I'm showing 6 of them here. I mentioned spectroscopy. There's a very, very powerful technique called dual comb spectroscopy that's been around for over a decade. And you kind of get the idea here. There's 2 combs are, they have slightly different repetition rates. Sample something like a gas cell. The 2 combs are mixed together on a photodetector. And what it does is it transfers optical information, optical absorption information down to a radio frequency signal. And then that can be FFT'd to actually measure the optical domain. And this is done with really high resolution. And so it does not require, large mechanical spectrometers. It can be done, really compactly. Dual comb LiDAR, it's kind of a way of combining the best of time of flight and interferometry. Data transmission, where the comb lines are used as WDM channels. And then this very interesting astrocomb application that we found ourselves involved with in the last 6 years with astronomers. Basically in the search for exoplanets, one of the most powerful techniques is to measure weak Doppler shifts in stellar spectra caused by the wobble in the center of mass motion of a star, a distant star like our sun. And it turns out that the only instruments, the only spectrometers that are now able to provide the kind of long-term stability necessary to look for these very, very weak shifts are frequency combs. And so over a decade ago, the idea of astrocombs came into play. Microcombs, it turns out, are really ideally suited for this application because astronomers, in calibrating their instruments in observatories, kind of the sweet spot for this, for their, for this application, is the K-band. And the K-band is something that is, in terms of repetition rate and line spacing, it's very naturally available with microcombs, solid time microcombs, because of their very small size. Same is true for LiDAR, same is true for spectroscopy. A lot of these applications benefit from this higher microwave, K-band, even millimeter wave repetition rate that has not been accessible, it's been very difficult, using conventional tabletop combs. And so, so really interesting is that the little microcombs are bringing more than just miniaturization, they're bringing a new feature, an important new feature and capability to these applications. But the two big ones that I mentioned over here, the synthesis and the clock, let me touch on those very briefly. These have really pushed the technology to the, to the limits, I would say right now. It's kind of to the current technology limits on integration, as you'll see. And so let's look at the synthesizer first, and I'll kind of skip through quickly the clock. But again, the synthesizer is going to take a radio frequency signal. It'll be a maser in the case I'll show you. And it's going to transfer it up to create frequencies on demand in the optical domain. This project is just finishing right now. It's run about 6 years, and it's been a big collaboration between a number of different university teams. And this is kind of a diagram of how this works. It actually uses two microcombs to do this. And this, some physics associated with comb formation. This is a better way to do this in terms of reducing power. But all of the components for this were actually generated, including all of the CMOS control, the 3.5 lasers, and the tuning and so forth. And this is what it looked like. There are 5 key chips. And the spectra for the 2 comb chips are shown below. So this is the octave spanning comb that I talked about earlier. This is a silicon nitride comb. There's a little comb in here that we actually fabricated at Caltech, and this is a silica comb, and its job is to give you the microwave, detectable microwave rate. And this is an old picture, and actually there's a much better picture of this that is a more advanced version of this. It looks very, very nice, and it's just coming out of John Bauer's group in Santa Barbara, about to be delivered to the agency that was funding this work. And so it has everything in it. It has the combs, it has the CMOS, it has the pump lasers. It's a completely, it's a really a functional device and doing the synthesis. But at the time of that sort of picture, we had the parts laying around on an optical table, and those parts were tested at NIST. It was in the group of Scott Diddams and Scott Papp. And you can see what they did in this case. They actually were testing this little microcomb-based synthesizer against a fiber comb-based synthesizer, and showing that frequencies could be generated on demand. This was another test. This is one I really like a lot. This is showing that it was possible to program in 16 hertz shifts in the output optical sine wave. And you've got to remember that this is not relative, this is absolute. What they were using in this case is that they were driving the fiber-based synthesizer and the microcomb-based synthesizer with a maser. So it's really a very, very nice radio frequency signal. But in this case, they were showing that they could indeed synthesize with incredible accuracy and precision, these optical sine waves, using this device. All right, real quickly, I'll do this in just a minute. But here's the clock application. So you're starting with an optical reference and trying to create a new reference for the second. This was another large application or another large collaboration reported out a little while ago. There are now whole new efforts. This was a rubidium reference. This was a thermal clock reference. And these are now being replaced with cold atom references. And but if you're curious, you can look at a report out on that rubidium reference just 2 years ago, and it just showed that the idea actually works. And so I'm going to wrap up here just in the last couple of minutes by just looking at the outlook. And so my outlook is a short-term, long-term. All right. So short-term, question is, what's the impact going to be of these little microcomb systems? And because as I wanted to say, as I said earlier, conventional frequency combs are already really very advanced systems. They're rack mount, they're commercial. If you want to do a laboratory experiment, they're kind of the go-to platform, I would say. And so, how is this going to work, in the future in terms of these new, microcomb systems? Well, I think the way it's going to work is that the rollout of the microcombs is going to happen probably in the short term in application areas where the size, weight, and power is going to be most important. And I've already mentioned the astrocombs, and astronomers would love to have these systems in space, in orbit around the Earth. And so this is likely going to be an interesting application area. There's already, some groups that are thinking about how to do this. And it improves, the resolution, makes it much easier, to look for these Earth-like planets around stars like our sun. Another area will be clocks. I've already mentioned that the new optical clocks, they will be the time standard of the future. We already put clocks in space, for GPS systems. And it's quite natural, and it probably will come to pass that, we'll have advanced optical clocks, perhaps out here, I'm showing a constellation of them that are being used to sync up GPS clocks. Or these clocks could be deployed around the whole solar system, and they could be used, as navigational tools, or even for science, gravity wave detection. There's even, these kinds of ideas about how they could be used for dark matter detection. So that's the shorter term. The longer term, and I'm thinking more on a time scale of decades, kind of comes back to this overall message of the talk of unification, spectral unification. So this is a plot where I'm showing frequency on the vertical axis, radio all the way up to optical and even higher. And here's, time going all the way back, to the 19th century and then coming forward. Each of these divisions represents 5 years. And so this kind of replays the original part of my talk. Electronics and optics, many, many decades, they were separate. Beginning in the 60s, groups started to work towards coupling the two worlds together. The frequency comb, brought about the unification. And now looking to the future, the really interesting thing to speculate upon is what will be the impact of little microcomb systems. And I think the impact to all of us in this subject is really very clear right now, is that in the future, decades in the future, engineers are not going to be designing with the idea that optics and electronics are separate. They're going to be running and designing, perhaps at the breadboard level, maybe at the circuit level, the chip level, in a more unified sense. In fact, there'll be a component, that will probably become a standard component that will provide a bidirectional coherent link between the electronics and the optical trains, that are on the system. What the ultimate impact of that will be on technology, it's really unclear, because you don't know until that happens. It's very much like, I like to present the analogy of the smartphone. Before the smartphone, it was impossible to foresee all of the ways it would help us and all of the applications that would emerge. The smartphones have clearly revolutionized, the consumer market. And I think there's going to be something very similar to that could potentially happen, once these, this full unification can take place at the chip level. And so I close by just thanking, the students I've, had the opportunity and, benefit of working with and a pleasure over the years. Also, I have a lot of really great collaborators that are fun to work with, and a lot of their work has been presented today. And thank our sponsors. And then, I conclude by, I hope this has been interesting and useful for you. There's a couple of recent reviews in case you're interested in looking a little further at this subject. There's a very, very nice review on microcombs, and there's a recent review on frequency combs that gives you this sort of higher level picture of the applications. And again, I want to thank you for the invitation to be at Calgary today virtually. And I hope the next time I'll be able to be there in person. And so thanks again. And I'm not sure if we have any time for questions, but I'd be happy to take any questions if there are any. So.